Good evening. Welcome to the 2024 Exploring Space Lecture Series, sponsored by Aerojet Rocketdyne and United Launch Alliance. I'm Matt Schindel, Curator of Earth and Planetary Science here at the Smithsonian's National Air and Space Museum. This year, we've lined up 4 speakers to talk about one of my favorite types of missions, sample return missions. Over the course of 4 lectures this year, we're going to explore what we've learned from samples returned by human and robotic missions to the moon, comets, asteroids, and what we aim to learn when we can bring samples home from Mars. The ability to reach out into our solar system and bring back pristine materials is something that people of previous eras could only dream about. This has been a reality for only half a century now, beginning with the US Apollo and Soviet Luna missions that brought lunar rocks and soil home for study in laboratories around the world. And in this short time, these samples have transformed our ideas not only about the moon, but about the history of our solar system and the formation of the planets, and yet many questions still remain. As our speaker tonight, Dr. Barbara Cohen, will tell us, gathering more lunar samples, or studying those samples in situ in their lunar environment, is one of the most important reasons to go back to the moon today. She has also seen how improved instrumentation and the evolution of planetary science over the years since Apollo have increased scientists' ability to extract knowledge from the samples that we have already on Earth. NASA recently released previously sealed samples from Apollo for research in laboratories with today's best instruments. This work is being done in anticipation of the Artemis missions to return humans to the lunar surface, to locations both distant and different from the 6 Apollo landing sites. These are some of the oldest and coldest places in the solar system. Dr. Cohen is a planetary scientist at NASA Goddard Space Flight Center. She is a planetary scientist who applies geochronology and geochemistry to planetary samples from the moon, Mars, and asteroids. She's been a member of the science teams operating the Mars rovers Spirit, Opportunity, and Curiosity, and Perseverance, and she participated in Antarctic search for meteorites in 4 seasons, where she helped recover more than 1,000 pristine samples for the US collection. Asteroid 6816 Barb Cohen is named for her. She's a principal investigator on multiple NASA lunar missions leading up to the Artemis landings, and she is the Artemis 4 project scientist. This evening, Dr. Cohen will be presenting her talk To the Moon and Back, and it's my pleasure to present Dr. Barbara Cohen.
Hi, everyone. Thanks for having me. I'm so pleased to be here. That was just the perfect introduction, showing all of those great photographs of how we collected those lunar samples on the lunar surface. I'm going to tell you what we've learned with those samples, and I'm going to tell you just at the end a little bit about how we're going to go get some more. So my name is Barbara Cohen. I am at NASA Goddard. I'm a geochronologist. That means I like to open up rocks, look at the isotopes of all the elements, and tell how old those rocks are. That helps us understand the history of planets. It's one of my constant amazements in life that I can take apart these samples and look at these tiny, tiny amounts of minerals and elements and isotopes and extrapolate that wildly to the formation of the solar system, the building blocks of the planets, our understanding of the universe itself. Samples are really, truly what keeps me in science and making these discoveries, so I'm very excited to share those things with you today. I am also the sample integrity lead for the Artemis initiative. So as we go back to the moon to stay, we will be collecting samples, doing field geology, taking new images, of course, all of the things, deploying the instruments, learning about humans living and working in space. And so it's my great pleasure to be helping with that enterprise, and I will be the project scientist for Artemis 4, so coordinating all of those efforts for Artemis 4 is going to be just a super great challenge, but something that I feel really passionate about too, so look out for those things to come. Let's go to the first slide. The thing about sample analysis is that the story of a rock, the story of a planet is really told through its rocks. And that tells us all about the history of the planet, how it formed, how it got put together, and what it's gone through. Do we have that movie? Can we bring the movie up? Great, thank you. So I'm showing you about all these planets that you know and love in our solar system. None of these are the moon, of course, but the moon acts like a planet. The moon formed like a planet. The moon went through planetary processes, and the rocks that the moon is made out of, when we brought those back, those were our first samples from another planetary body that we intentionally went and took from another planetary body and brought them back and learned about planetary processes other than the Earth. And so the things that we learn about the moon through the lunar rocks at the time that we did this opened up all of these planets to us, told us what's in the interior of these planets, how their surfaces formed and evolved in ways that we had never been there. We had never seen how they, worked, but the lunar samples are what really opened that up. So the thing about samples that I want to convey to you, and this is going to be true for this whole series as you learn about all of these other samples, is that we start with a defined set of elements. All of the elements in the solar system were created when the solar system formed, as the elements that were in the universe coalesced and formed our sun and formed our solar system. Those elements, that's physics. Like, we're finding new elements, but the elements are the same all across the whole solar system, all across the whole universe. There's nothing on the moon or on Venus or on Pluto that's an exotic element that we've never heard of. We have a set of elements to play with. They're kind of like the letters in our alphabet. Those elements, because of physics, combine in very specific ways. We know how they combine when we share electrons or we have covalent bonds. Like, those are the ways that elements work together to combine. That's physics, and so we can understand how they're likely to be put together in other places. That changes a little bit with the specific conditions on a planet. So as temperature changes or the amount of oxygen changes, then we can get them to combine in a little bit of a different way. That's the real fun in mineralogy, where we can trace those chemical combinations back to the physical processes that led to them. And then those minerals combine into rocks. That's what we think of when we think of a sample. We think of a rock. It's made out of those minerals that are in specific ways that we know. And so the rocks that we have in our solar system are also predictable. And so when we get a rock back, we may not know exactly what it is, but that's the forensic geology that we do. That's when we take that rock apart and say, okay, I know that the elements were this and the minerals had to be this. That means the conditions had to be such that we got a sedimentary rock, or we got a metamorphic rock, or we got an igneous rock. Those are ones that you probably know and love. We also have impact rocks. We have things that form deep in the mantle or on the surface. So taking those rocks apart is really how we learn what those planets are made out of, and all of the things that we see on other planets form by those same processes, and we use those same kinds of interrogation techniques. Okay, let's go to the next slide. So mineralogically, lunar rocks are pretty simple. Common lunar minerals include things like plagioclase feldspar, pyroxene, olivine. Don't worry if you don't know those mineral words, that's okay. They're things that if you have a granite countertop, you have these in your life. If you go out to any rock that you pick up while hiking, you have these minerals in your life. They are made out of oxygen by weight, 50% oxygen by weight. They also have things like calcium, aluminum, magnesium, iron, things that are very, very common in the crust of the Earth, are very common in the crust of the Moon, very common in the crust of Mars and Mercury and Venus and all the planets. So those are because that's how silicon and oxygen combine, and then we get these other little cations that come in according to the conditions. So the Apollo and Luna samples, came to us from the Soviet Union by robotic sample return, and now, of course, we have Chinese sample return with the return of the Chang'e 5 samples. All of those return samples came to us from known locations on the moon. So again, the moon is a planet. It's got different kinds of terrain and different areas. Going there, taking the sample and bringing it back provides us with that tie to that specific location, and therefore the specific history of that location. So that's how we learn about the different history of the moon. And they tell us about the environment, and we'll see that the environment that the moon went through is the Earth-Moon system. You can think of the Earth and the moon as a system, and we'll see why in a minute. So all of those things that tell us about the moon also tell us about the Earth and the moon, and then we're going to learn about how it expands into the whole solar system. So next slide, please. So tonight we're going to talk about I didn't make a top 10 list. It ended up being 8, just so that we have time for questions at the end. But we're going to learn about the top things that we learned from lunar samples themselves. And again, remember that a lot of these samples came back before we knew much about planetary science in general, before we had many of our science missions, before we sent anything to Mars, before we had sent anything to Venus or to Mercury. We had the Voyagers that went to the outer solar system, of course. These were before all of that. These were our key to the whole solar system, our key to understanding everything. And the great thing about samples is they are the gift that keeps on giving. We study these samples for all of the years leading up till now. We get 100-ish requests every year for lunar samples, for new active research. And that is because our techniques on the Earth keep evolving, right? We keep getting better techniques. Medical techniques actually have a lot in common with lunar sample techniques as we get better imaging, as we get down to smaller and smaller sample sizes. We can take things apart and learn more about them in ways that we can't send another Mars rover all the time, right? We have the samples here, we can take them into the laboratory and learn new and different things about them with our new and different techniques. So some of these things that we're going to talk about today are things we learned immediately from the lunar samples, and some are things that we've learned even as recent as the last 2 decades. So we're going to talk about each one of these. The moon is ancient. The moon formed in a giant impact. The interior of the moon is differentiated. We'll talk about what those words actually mean. The moon is covered with impact craters. The moon lost its heat by volcanism. Lunar samples form an absolute time scale. That's my jam. The moon carries a history of solar activity, and the moon is lifeless but contains the building blocks for life, which is pretty intriguing. So let's go to the next slide, please. The moon is ancient. We did not know how old the moon was before we went there and got the samples back. We did have meteorites. People were working on meteorites, and meteorites are very ancient. Meteorites date the very beginning of the solar system as the sun was forming and the solar disk was collapsing into planetesimals and planets. We do have the meteorites that showed us that the solar system is about 4.56 billion years old. So we did know when the solar system started to form, but the oldest Earth rocks that we have are a little more than 3 billion years old. So we had a real big gap there, 3 billion years to 4.5 billion years. We don't have any Earth rocks, and we didn't have any other rocks. We had meteorites that were super old, and then Earth rocks. The moon rocks filled in that time scale for us in a way that was revolutionary to understanding the whole solar system, how it formed and evolved, how all the planets formed and evolved. So up on the top there, what you see is a time scale across of the different planets, Mercury, Earth, Moon, Vesta, and Mars. The moon is where we really anchor all of our time periods to, but we have these epochs for the other planets as well, and we'll talk about how we got those. But very early in the solar system, we had giant impacts. Then you can see possibly a window of habitability, and then you can see planetary heat loss along the bottom. That's mostly by volcanism. The reason why we can put those numbers across the top is from the lunar samples that we went and got and brought them back and opened up in the laboratory and could date them. So we could date when giant impacts happened. We could date when planetary heat loss and volcanism happened. And then we can look at the other planets and by analogy understand when they went through those same processes. And we had a moon rock called the Genesis rock that really told us how old the moon was at 4.5 billion years, which is just after the age of meteorites, but older than any known Earth rock. And we have moon rocks that populate that whole time period that the Earth has lost. We've lost that history on the Earth because we have plate tectonics and oceans, and we recycle our crust. And so that is no longer available to us, but is all available on the moon in the lunar samples. Let's go to the next video, please. The Earth and the Moon formed together. This is something that we call the giant impact hypothesis. It's a hypothesis because it's still an active area of research. But before we brought the lunar samples back, we didn't know how the moon came to be around our Earth. You can go look at it. It's not the same as the Earth, right? It doesn't have plate tectonics. It doesn't have water. It's not our twin. So how did we get the moon? Mars got its moons probably by capture. The outer solar system planets probably got theirs by co-accretion in a disk. Actually, the way we got our moon is because as planetesimals were forming in the solar system, that means as things were sort of coalescing around the sun and condensing into solid planets, those planets were not the planets we see today, but planetesimals, smaller planetesimals, and they started whizzing around into each other and colliding. This turns out to be a really common process. Like, we did not understand this before we went and got the lunar samples. The lunar samples show us that the Earth and the Moon rocks are incredibly similar to each other in ways that would be very difficult to understand if we had captured the moon from some other place. We use things called oxygen isotopes. So they are the same element, oxygen, but with different numbers of neutrons in their nuclei, and those are a fingerprint. Those are a unique fingerprint to where in the solar system they formed. So we can tell, for example, for meteorites that come from Mars, why they come from Mars, partly due to their oxygen isotope signature. The oxygen isotopes between the Earth and the Moon are identical. That means that we have a common history. We share a common history, and that common history is when planetesimals collided, the Earth and another planetesimal collided and formed the moon in that smooth particle hydrodynamic simulation that you just saw. That was a big, big deal. That means it wasn't captured, it wasn't fissioned out. It's not like the Pacific Ocean has a big hole in it because material got knocked out. You laugh now because it sounds funny, but those were real scientific hypotheses that were being entertained. And the evidence that we got from the lunar rocks is what really nailed down our present understanding. And that, when we see that Venus is rotating backwards, when we see that Uranus is tipped on its side, those are from giant impact events that happened very early in the solar system. But who would guess that unless we had something to point to? And what we have to point to is the existence of our moon that shows us that these giant impacts happened early in the solar system. Okay, we've got another movie coming up. The moon is differentiated. So I said I'd tell you what that means. It means it has a crust, a mantle, and a core. And this movie is showing you how that happens. The moon was molten after that crazy event that you just saw where everything collided, a lot of energy, everything melted, and then formed the moon. Now, when something is molten, when molten rock is molten, you know it as magma or lava, right? Think about ice. When ice is molten, you call it water, and then it crystallizes and forms ice, right? Same thing with rock. When rock is molten, it's magma, and when it crystallizes, it forms minerals. And when it crystallizes inside the moon, it's what we call differentiation. The minerals that are heavy sink to the bottom, and the minerals that are light float to the top. It happens that the moon has these light elements that form the crust of the moon. So the crust of the moon that we see today, that's all light-colored, white, gray, those are the minerals that formed in that giant magma ocean, and that differentiation that floated to the top and made a crust. And then other minerals sank to the bottom and formed a core. The moon has a crust, a mantle, and a core. The Earth has a crust, a mantle, and a core. What do you think Mars has? What do we think Mercury has? What do we think all the planets have? A crust, a mantle, and a core. We thought maybe that was unique to the Earth, but then we saw it on the moon. We can see that in the lunar samples, that some of them come from the mantle, some of them come from the crust, and those minerals have separated in a way that we can understand by this process of differentiation. That helped us understand all planets go through this process. And even some big asteroids. Vesta probably is differentiated, in Ceres as well. Okay, the next movie is going to pick up where differentiation left off. And we've got this nice magma ocean that's now crystallizing here in the movie. And you can see how it forms a crust, that nice gray-white crust that we're so fond of. And that's a really nice moon there. And now we're going to beat it up. So as things were forming, we have that giant impact, but we still have things that are whizzing around the solar system and banging into planets and crashing into them, causing maybe not giant impacts that form planets, but a bombardment. So we call this the late heavy bombardment or the lunar cataclysm. We're bombarding the moon with big, big basins that you see today. So when you look up at the moon today, you've got that nice gray crust, and then you've got big blotches that are black. Those black blotches are volcanism, as we'll see in a minute, but they're circular. They're circular because they're big impact craters, really big impact craters, continent-sized impact craters. And I promise you that every crater that you see on the moon today and in the past had a counterpart on the Earth. Nothing just comes whizzing in and decides to hit the moon and I'm going to stay away from the Earth. All that bombardment was happening to the Earth at the same time as it was happening to the moon. We probably had single-celled organisms at the time that that was happening. We didn't have multicellular life. We didn't have intelligent life. This is 4 billion years ago. But we probably had life on Earth. And if it went through that, what came out the other side? It must have been a really trying time, but our least common ancestor as humans was a hyperthermophile, something that really loved heat. Well, maybe there's a lot of heat that went into that bombardment. Maybe that's what came through the other side. So all of the things that we study on the moon had the counterpart on Earth, and that late heavy bombardment is one of the great enduring mysteries of research that we are still researching today. How did that period happen? How did it affect the Earth? How did it affect life on Earth? All of that came out of the lunar samples. When we were studying the lunar samples and looking at the ages of the impact craters that we saw in the lunar samples, and again, we don't have those ages for rocks on Earth. Those rocks on Earth are gone. We have those ages of impact craters on the moon, and that's what it told us, is impact history was just insane around that time. So we know that it was happening on the Earth even though we don't have the samples. We learned that from the lunar samples. All right, our next slide, we're going to talk about volcanism. When people first were looking at the moon and sketching the moon, and you've seen Galileo's sketches of the moon, and many people sketched the moon, and you know those big black blotches are called mare in Latin, and that's for seas or oceans. They're not oceans of water, as we know now. I don't think that, even in the era of Apollo, we did not think that they were oceans of water, but what were they oceans of? We did not know. What we know now is they are lava flows. So we went and we picked up the sample and brought it back, and now we can tell what it is. They're lava flows. They're lava flows not like Mount St. Helens, where it forms a nice cone volcano, but more like Hawaii, where it's very fluid and flows out. And so when it flows out, it just flows into the lowest parts that it can go into, and those are those big basins. So we have those big circular craters, big bowl-shaped craters. The lava flowed into those, and that's why you can see big craters filled with lava on the moon. This is a close-up image of just one of those mare regions, and you can see all sorts of volcanic constructs and ridges and little channels and things like that. The mare, or the basalts that we see on the moon, we have so many of them that we can date. When we get them back, we can understand their composition to know why they're fluid. They're very iron-rich. We can tell their ages, and so we know when volcanism happened on the moon. And so we know that the moon lost its heat primarily by volcanism. So when we saw it differentiate, that's because it had so much heat. There's not a lot of heat flow right now. We did measure that. And so that planet had to lose its heat. The moon had to lose its heat. It does that from the inside. The Earth loses its heat by plate tectonics. The moon lost its heat by volcanism. So it had to spew the hot interior out onto the exterior and have it cool. And so we know how long that happened because we have the dates of the rocks on the moon. And when we look at places like Mercury or Venus or Mars with these lava flows and these big constructs, because they also don't have plate tectonics, we use the moon and the things we learned from the moon rocks to understand how those planets lose their heat as well. All right, the next slide. I have to show you a couple complex slides, I'm sorry. This is my favorite graph. This is called my fave astro plot. So this is my actual area of research, which is on the y-axis, going up the y-axis. That's the number of craters. So if you look at a surface and you can count the craters on the surface. Along the x-axis, that's along the bottom, is the absolute time. So that's what I do in my laboratory, is I give it an absolute age. I open up that rock, I measure the isotopes, I say it's 3 billion years old. The moon is the only place, and even when you hear about comet sample return and asteroid sample return, we can't do this with those samples. This is the only place where we can count craters on a surface, and we can tie it to the absolute age of the sample. When we look at Mars, all we have are the craters on the surface. When we look at Mercury, when we look at Venus, when we look at the outer planet satellites, we don't have samples from them. We have the number of craters on their surface. So when we can count those craters on the surface, we can use this graph to understand how old those surfaces are. And so we can put them in order, and we can say what came before what. This igneous volcano came before this sand dune covered area. That's how we can put other planets in order. It's all because of lunar samples. So we have samples from young craters that you can see here on the right, like Copernicus and Tycho crater. You can see our old samples that we have there on the left. There's that Chang'e 5 sample right in the middle. That was a really important sample for science because it's right in the middle there. So this graph tells us that there was really heavy bombardment very early in the solar system history, around 4 billion years, that's what we talked about, and then it dropped off later. And that tells us how to date other surfaces. This is the only way that we can do this, and it's all from lunar samples. And you can see, because you've got Chang'e 5 in there, right? This isn't just from the Apollo era. This is decades of studying those lunar samples with better techniques to be able to get those ages decades after the samples came back. And the next slide is another scary slide. So it's going to show you all of the processes that happen on the surface of the moon. So the surface of the moon doesn't have an atmosphere like we have, and it doesn't have a magnetic field like we have. It has what's called a surface-bound exosphere. So I'm taking pictures of my scary slide. It has a surface-bound exosphere, and what that means is that there are molecules that bounce off the lunar surface and hang out in space for a while and then come back down. And while they're sort of bouncing in space, they form a transient exosphere, or a transient atmosphere. But it's a constant process, and so we have an exosphere, a very thin number of molecules in the lunar air at any time. What that allows us to do is to look at how the sun directly interacts with the lunar surface. So the lunar samples contain not only evidence of the lunar past, of the Earth-Moon past, of the solar system past, but the past of the sun itself. The solar wind is directly interacting with lunar samples. It directly interacted with lunar samples for their whole history. So if we have lunar samples that we can tell were under something, like under a boulder, and we know when that boulder got there, then we know what the sun was like at that time. So we don't have a history of the sun. We can't go measure the sun back in time. The way that the sun delivers the solar wind and the way that it sets up some of these complex interactions that you can see here allows us to tell the history of the sun itself, which I think is pretty cool. Okay, the next slide is our last of the top 8 things. Here are the Apollo sample sites, and the Luna sample sites were along those as well. The moon contains organic material that comes from micrometeorites hitting the surface of the moon. In these permanently shadowed craters here at the pole, far from the Apollo sites, you heard in the introduction that these are some of the coldest places in the solar system. These are places where the sun never goes directly overhead. If you've ever thought about Antarctica or the Arctic, where the sun goes around the horizon in the summertime, or if you've ever been in a city like DC or New York where you're between tall buildings in the wintertime, you know the sun doesn't go directly overhead. And if you've got ice, snow that hasn't been cleared from those areas, you know it sticks around a really long time because that sunlight doesn't get there to melt it. That's what's happening in these craters. The sun doesn't go overhead. You can see how they remain dark. The sun is going around the horizon. Those places are really cold. They're like 40 Kelvin, 40 degrees above absolute zero. That's colder than the surface of Pluto. It's right in our backyard. Those are places where these molecules can collect over time. So if they're delivered by asteroids or comets or micrometeorites, organic material, water, things like that, they can collect in these really cold areas over a long time. We know that the moon is lifeless. There's no bugs that are going to come get us. There's no super virus. We have the lunar samples. We know that they are biologically sterile. But the building blocks for life are also really important to understand. And if we want to try to measure life on, say, Mars or Europa or places like that, we need to be able to understand how water is not life and organic materials by themselves are not life. So the moon is kind of a witness plate for us, where you can send our life detection experiments, measure these things that are there, but come away with an answer that it is not life, so that when we go to places that may actually have life, we can understand how better to do that. That also tells us that the moon has these really abundant resources. So having the water there, having this abundant sunlight, you can see the crater that we're looking at here in the center. You can look at the rim. It's lit almost all the time. Sunlight is something really important if you've got solar panels, and they can be lit all year round. That's a really good resource for humans to use. Water can be a really good resource for humans to use. So if you want to go live off the land and not have to bring everything with you, these are really great resources. And one of the reasons why we'll see going to these polar regions is important for our next phase of lunar exploration. So the next slide is going to talk about the next phase of human exploration on the moon, which is our Artemis program. So can you show hands? Who's heard of Artemis? Have you heard the name? All right, you guys are mostly in the know. Artemis is our program to send humans back to the moon to stay, right? So this isn't flags and footprints. This isn't show the Soviets that we're the superior power. This is learning to live and work on another planet. This is bringing cislunar space into our economic sphere and expanding those opportunities for all of Earth. So landing humans on the moon is just sort of shorthand for all of these things that we want to do. But we are sending humans to the south pole of the moon, maybe not the geographic south pole, but the south polar region, for those reasons we just talked about. That's where the water is, that's where abundant light is, and also it's somewhere where maybe we haven't been yet. Maybe we want to learn more scientifically about a place that we haven't been. So on the lunar surface, we're going to look for those natural resources, and we're going to work with industry together. You've seen a couple, IM and Astrobotic recently, sending landers to the moon. That's our very first phase here on the left-hand side, where we're working with industry to start sending landers to the moon. We'll see Artemis 2. You saw Artemis 1, right? You saw Artemis 1. We'll have Artemis 2 coming up next year, and then Artemis 3 will be our first mission to the lunar surface. It's going to look more or less like Apollo 11 did, where it's a test mission. There's going to be a lot to learn about our systems, about our engineering, about how we're going to be able to walk around on the moon, how the suits are going to work, things like that. But it's not test for science. It's real science. It's really important science. So even though it's testing for engineering, as soon as we get boots on the moon and we can start doing real field geology, which means looking around at the relationships among the units on the ground and taking those images, taking those observations with the crew's eyes, and taking the samples and taking them home with us and opening them in labs. That's real science of a place we've never been, and we have a lot of questions about those lunar poles. So we're real excited about that. And next slide just highlights some of those science that we want to understand. And these should look familiar to you by now, because these are the things that we want to learn about the moon, that we want to learn about every planet. But at the south pole of the moon, these are really unique opportunities for us to learn about the pole of a planet. We've never been to the pole of another planet except for with Phoenix on Mars. And so being able to do the field geology there, to drill into the subsurface, studying planetary processes, of course, always understanding volatile cycles, the water, the organic materials, the impact history of the Earth-Moon system, which is always great to see for me. Understanding the ancient sun, again, understanding how the ancient sun interacted with the Earth-Moon system, and a platform to study the universe. These are places where we can set up very quiet, radio quiet telescopes using the moon to block the radio transmissions from the Earth. So these are all things that are uniquely enabled by going to the south pole of the moon. Before we do that, the next slide, before we go back with Artemis, we had a kind of a practice run with our sample analysis techniques. So one of the real questions that we had is that the Apollo samples and the Luna samples came back 50 years ago. We don't have those same people running our labs anymore. We have people like me in the lab. So are we really ready? Is our community ready for new lunar samples? Are we ready to do this? Are our laboratories ready? So yeah, we heard that we opened the samples. We opened a sample from Apollo 17 that had never been opened. It came back to us as a drive tube, which means a tube that they hammered into the surface and pulled out, sealed on the surface of the moon. And then as soon as it came back to Earth, they put it in another sealed container. And it has never been opened since then. And so this was our first chance to open that up. We extracted all the gases from it. These are the curators up here on the right-hand side. You can see them opening it up in the glove box. And down there, all those happy smiling faces, that's my team who got pieces of that drive tube that we were able to study in our laboratory. And in fact, we're giving those first results at the Lunar and Planetary Science Conference literally next week. So we're very excited to have been a part of this. And I think the answer to that was resounding yes, we are ready. We're very excited for the new lunar samples. And it's because it's not just lunar samples. And if you come back to the other lectures in this series, you'll see how we're applying these same techniques and these same new laboratory developments to things like Stardust and OSIRIS-REx, and upcoming for Mars as well. So we're real excited for that. And the next slide is just gonna tell you what I told you, which is we had a lot of cool things that we learned from lunar samples, and we really want more. Samples are the gift that literally keeps on giving. And so, can we have that next slide? So the moon is ancient. The moon formed in a giant impact. The interior structure of the moon is differentiated. The moon is covered with impact craters. Moon lost its heat by volcanism. Lunar samples form the absolute timescale for the whole solar system. The moon is lifeless, but contains all the building blocks we need and creates resources for humans. And the moon carries a history of solar activity. Literally the gift that keeps on giving. All of these things we couldn't have learned without the lunar samples or some planetary samples. Happens we learn them from lunar samples, and we keep learning them. Some of these things we're doing in our laboratories right now, learning more. The samples that we get from the lunar south pole are going to open up a whole new world for us. They have different volatiles. They're from a different geologic terrain. We know so much more. We have ways of setting up hypotheses and asking questions that our new samples will be able to answer for us. And next month, I hope you know, there's a total solar eclipse. You can't have a solar eclipse without having a moon to eclipse the sun. So 2 weeks before the eclipse or 2 weeks after the eclipse are actually the best time to go look at the moon with binoculars, because that's when you can see the terminator itself, and you can look at the features along the terminator that get highlighted by having that partial shadow. So 2 weeks before or 2 weeks after that total eclipse, if you're chasing that eclipse, go out and look with binoculars at the moon and appreciate the moon that's about to go in front of our sun. And I think that I'll close with the video. So if you want to learn more about the Artemis generation and the things that we're doing to enable new samples, but also field geology and imaging and all the things that we need to do with crew to go back to the surface of the moon, I recommend this NASA series called NASA Explorers. All of season 5 is about the Artemis generation. So let's run that, please.
Well, thank you, Barbara, for a wonderful talk. I know we've probably got a lot of questions in the audience here tonight and also on the web, and folks have been sending in their questions via our YouTube feed. So those are right here in front of me. And then also, if you're in the audience and you have a question, you can make your way to the microphone that is there in the center of the aisle here, and we will call on you once you get there. And please don't be shy. It always takes a little while for someone to work up the nerve to get to the microphone for the first time, but you know, we're friendly, so please, you know, bring your questions to the microphone. And while we're waiting for that, you know, I want to ask a question of my own, which is, you know, in the 1960s when we were, you know, seeing the moon for the first time via spacecraft, you know, rather than through the telescope, and we saw our first images of the far side of the moon. That was surprising to a lot of folks who thought it would look pretty much exactly the same as the near side that we were so used to looking at, but it defied expectations, right? Because it wasn't as heavily cratered as the near side. What accounts for that? Why does the moon look different on the far side than the near side?
Why does the moon look different on the near side than the far side? It actually is more heavily cratered on the far side. We don't see that side. It looks different because there is less obvious volcanism. So I told you that those dark patches that you see on the near side, those are lava flows filling in giant craters. Those giant craters exist on the far side, but the far side crust is thicker than the near side crust. Why that is, ask a scientist. Ask 10 scientists, you'll get 11 answers. It's an active area of research why we have that crustal thickness dichotomy, as we call it. But the crust is thicker on the far side, and so the magma that was generated in the interior of the moon couldn't make it all the way to the surface to flow out over the surface. So there probably was magmatism. It probably just didn't get to the surface. And so it looks different to our eye because there aren't giant lava flows. But those lava flows are younger, the ones that we see on the near side. The younger the surface is, the fewer craters it has. And so actually the far side is more cratered than the near side.
It just doesn't have the really big dark marias.
It doesn't have the big dark splotches, that's right.
So we have a question from the web, and the question is, the collision that created the moon must have created many other objects, perhaps things like asteroids. Have we found any of those objects that seem to be from that source?
Yeah, that's a really good question. And in that simulation that you saw sort of blobs getting thrown off. The angular momentum of the system is such that all of that material got collected back in. So it all fell back in, and it all fell back in either accreting back onto the moon or onto the Earth. But that might have set up its own little mini bombardment where that material fell back in as that process finished up. It's possible that some of that material did get thrown off. A lot of it was vaporized and maybe lost. I don't think we would be able to identify that material, and I don't think there was probably that much of it, but it's possible.
All right. We have some questions in the audience. Would you like to ask your question, sir?
Yes, thank you so much for the presentation. It was a great discussion. My question is, you had mentioned earlier when you were answering the first question about an active field of study comparing the outer side of the moon to the inner side of the moon. Could you describe a little bit more about other active areas of study involving the moon, or areas of top debate right now that might shed some light might be shed from the Artemis missions? Thank you.
Absolutely. What are the active areas of research right now? One of the most active areas of research is the water that we see in various flavors on the moon. Where did it come from? Was it in the moon when it formed during that giant impact hypothesis? Did it come from asteroids and comets? Did it come from the sun? The sun itself the solar wind is mostly hydrogen. And I told you earlier that the moon rocks are half oxygen. So when you bombard hydrogen into oxygen, you can make water that way. The answer is probably all three of those processes and probably others as well. So how much of each reservoir came from what process? is actually really important if we want to know whether water on the moon is a fossil fuel that was created once and never touched again, or if it's a renewable resource that keeps being made. It's a really important question for us. We don't know the answer to that. We are pursuing that by lots of different methods. And going to the South Pole is really going to help us understand that as we get to places that are more likely to sequester more of those volatiles. Another thing that we don't fully understand yet is the near side and far side dichotomy. We have been pursuing that mostly with gravitational methods. So we had a mission called GRAIL that was looking at the gravity signature of the moon and the crustal thickness and the mantle thickness. That also has to do with the interior structure of the moon. Those are things that we have to get at by indirect methods. We can't take a deep drilling rig to the moon and try and get at what the 10-kilometer down structure is. We have to do that by these indirect methods. So something that we really would like to do with the Artemis program is send more seismometers. We sent seismometers with the Apollo program, and that gave us kind of a global view, but now we have these really more nuanced questions about the crustal thickness. So it's our intent to deploy more seismometers, more geophysical monitoring with the Artemis program, for example.
Great. So your answer to that question made me think about the fact that there are, all of these, remaining unknowns that we know are unknowns about the moon, and then also questions that have emerged through the research that's been done over the last 50 years. But what about surprises? How likely are we to be surprised by what we find when we go to this South Polar region and start looking into these permanently shadowed areas?
Entirely surprised. We can set up our best expectations, but nature always defies our imagination. That's always going to be true. One of the things that we're really actively researching is the late heavy bombardment that I talked about, where we had all of these impacts happening on the moon and on the Earth, and it was when single-cell life existed. As it turns out, when we look at those samples that gave us that information, they all came from the near side of the moon in that little restricted area. And we think that maybe it was just one impact now. So we set up this whole big thing about the solar system, and maybe that's only one impact. One of the great things about going to the South Pole is it's really far away from that one impact site. And so we can repeat the same kind of study, but with different samples, places. They came from different places, and we can really start to test that hypothesis. What's inside a permanently shadowed crater? We'd like to know, right? So how that's structured, whether it's an ice layer across the whole top, whether it's patchy, how it looks at below the surface, are they just adsorbed water molecules on grains, or are they ice skating rinks? We would love to know that. We're happy to be surprised.
Yeah, it's very exciting. We have a couple of more questions in the audience. Why don't we take the next one?
Hi, thank you for a great presentation. I love your skirt.
Thank you. This is Shorty Crater from Apollo 17.
Very cool. I was wondering why that drive tube was left unopened for so long, and if there's a bunch of other samples that they're saving for later, and why.
Yes. In fact, about 25% of the lunar samples were completely sequestered until such time as we deemed as a community to open them. That was entirely on purpose. It was entirely planned at the time, and it was because we knew new techniques would come available. We knew there would be new advancements in sample science, and so we wanted to save those samples for such a time as we could really study them a lot better. This was a good time to open that one, but there are many, many more that are not opened and that are sequestered. And we do that for every sample return mission, and you'll hear that with the other sample return missions as well.
We have a question from the web that would be, I think, a good follow-up from that, but you might not want to answer it in detail because it might be, giving some spoilers for next week's talk at LPSC. But one of the questions is, what are the most surprising things that we've learned from those samples that you've just opened and applied, the most recent instruments and techniques to?
Well, I can tell you just, I don't think any of you are going to the Lunar and Planetary Science Conference. Well, you'll have to be surprised at my talk. One of the things that we learned on our team is we found Almost half of the samples that we happened to look at were contained a mineral called spinel, which is a little bit of a rare mineral. It's formed very deep in the lunar crust, and it doesn't occur through many samples at all. And we found it in a lithology that had never been studied. I don't think it's necessarily a new discovery, but it was surprising to have so much of it. And it's a really great joy to find that and to go back into the literature and say, well, who else saw this kind of rare mineral? Does that mean that my samples are related to the ones that we saw on Apollo 11? Why would they be related to each other? Was there a common landslide, or did they come from the same impact? So yeah, that's the process that we go through.
Mm-hmm. And another question from the audience.
Hello. First off, thank you for the lecture. I guess you could say it was out of this world.
And we came back again, so.
That's just a sample of the puns. And now that I've turned the whole crowd against me, I noticed you had the slide about Artemis and the scientific research they want to do on the moon. And thinking about the turnaround time for your laboratory to, go up, get materials, bring them back down, then do the research. Is the goal for eventually your lab, to basically be on the moon doing research?
Oh my gosh, yes, I have a whole research program dedicated to sending my lab to the moon. I think that we need both in situ instruments and the Earth laboratories. If you follow the Mars rovers, we have the best remote sensing and in situ techniques that we can develop on the Earth that we send on those missions. But they can't change, they're static, and they can't get any better. And when we make a flight instrument, we have to make compromises that we don't make in the laboratory. My laboratory plugs into a 240 volt big power thing, whatever, and it's huge, right? It takes up the whole room. And so I can't take that to the moon. I have to make it smaller, lighter, more power efficient. All of those things come with compromises to the precision that you can get out of the instrument. So places like the permanently shadowed regions, maybe those are places that we don't want to mess up by putting humans there, or maybe we can't access with humans. So robots and in situ techniques absolutely have a place there. If we really want to get the difference between samples that are 4.3.894 billion years and 4.3895 billion years, that's not currently within our reach with in situ techniques. That's why laboratory analysis is needed. So it's not either or, it's definitely both, and we are definitely planning for instruments to go along with Artemis.
From the web, we have a pretty specific geologic question from someone who obviously knows the history of Apollo and the history of lunar geology.
So you're going to stop me on stage.
Yes. They say Apollo 15 visited an area with a rill, and at the time, rills were believed to be collapsed lava tubes from the volcanism era. Is this still believed to be the explanation, and does that fit into sort of the history that you showed us?
Yes, and yes. We do believe that rills are collapsed lava tubes because of that fluid nature of lunar lava flows, because they have so much iron in them. They get really runny and they run out a lot, and so there aren't that many conduits that we can see, but those rills are probably one of them, and then as they collapse, they can form skylights, or they can form the rills that you see.
Great. And we have another question in the audience.
Thank you. After the Apollo mission, a number of the lunar samples were contributed all around the world by President Nixon and possibly others. If someone came to you with two rocks and said, can you, is one of these from the moon, can you always tell which one is and which one isn't? And if so, in as lay terms as you can, how can you tell that something really came from the moon or it's a fake?
Yes, you can tell. I mean, I can't tell by looking at it necessarily. I guess maybe for some rocks I could, but not necessarily. If you picked up a lava rock in Hawaii and compared it against an Apollo lava rock, they're very, very similar looking. You can always tell with laboratory analyses because moon rocks are drier than any rock that you could ever find on the Earth, and they have no organisms in them. Any rock that you pick up on the Earth, even a fresh lava flow from Hawaii, has water in it from our atmosphere, just water touching it, just collects on it, and it's got bugs in it. They all do. Pollen or an insect or, a single-celled organism, every single one of them does.
Thank you.
Another question from the web. We know that the most recent period on the moon is the Copernican period, and the craters Copernicus and Tycho are these incredibly well-defined craters that look exactly like an impact crater is supposed to look, right? But what is the youngest crater that we know of? I mean, I know craters are, very small craters are being formed a lot on the moon, but what about the bigger, more noticeable ones? What's the youngest of those?
Well, Giordano Bruno is one of the youngest craters that you can see in binoculars that's fairly young, and there have been papers written about that, and forgive me, I don't know the exact number. But if we're talking about spacecraft, the Lunar Reconnaissance Orbiter has many images online that you can go look at that are change comparison, that see very recent impact craters that are in the order of 10, 50, 100 meters across. And we see those happening now in our lifetime that we can see on the moon as the moon changes under the Lunar Reconnaissance Orbiter.
Wow, fascinating. We have one more question in the audience. Please.
Hey, I have a really simple one. You say there's water. How much water?
Good question.
Well, that's an active area of research. Why don't you come join my research group and we'll find out. How much water? We don't know. I mean, I'm being a little facetious, but honestly, we don't know. There's different kinds of water. If we think about the Earth, how much water is there on Earth? We think about how much water there is in the oceans. That's one number if you were just looking from space. But we also have water in underground reservoirs. We have this water, this contributes to the water budget. The water in my cells contributes to the water budget, right? So it depends a little bit on what you define as what the water is. On the moon is very similar in the sense that it's very complex. So we don't have oceans and we don't have rivers, I'm not suggesting that, but there's water in the minerals themselves that probably came from the interior of the moon as they erupted and formed. There's water that's on the surface that we see as single molecules that probably comes from the interaction of the solar wind. Those two sources aren't very much. You couldn't wring out lunar regolith and drink it. It's interesting scientifically, but it's not a whole lot. But in those permanently shadowed craters, there could be a lot. There could be tons, I don't know, megatons, I don't know how much. There could be a lot that you could mine and use potentially.
Like a lake?
More than that.
I mean, frozen lake.
Yeah, yes. But probably not like a skating rink. So we have looked at them with radar, and radar would bounce off a skating rink and come back to us with a coherent signal. So that work is actually done by people here at the Smithsonian. So probably not a lake, but a lake's worth of water, conceivably, yes.
I think we have time for just one more question, and this question I'm going to modify it a little bit because I think the first part is more a question for me to answer, which is, how do you decide which moon rocks people get to touch here at the National Air and Space Museum? And the answer to that question is that we get those rocks on loan from NASA, and NASA decides what rocks we can put out for you to touch so that you can touch the moon here at the museum. So I'm going to change that question to, can you get us a rock from the lunar South Pole that we can touch here at the museum?
The great thing about the U.S. collections, and this is true for the lunar rocks, the Apollo rocks, it's true for the Antarctic samples, we mentioned the Antarctic samples, it's true for the Stardust rocks and the OSIRIS-REx rocks that you're going to see, and it will be true for the Martian meteorites, or for the Martian rocks, is that those collections are open to everyone. They're a U.S. national collection that are open to everyone in the whole entire world. You have to have a really good reason. You have to send in an application saying exactly why you need it and exactly what you're going to do with it and why you need it to be that specific sample. It goes to a committee of experts that judge all of those applications and judge whether it's a good reason that they should give you the rock. But I promise you, anyone in this audience, you could write an application if you had a good reason, right? But those get considered by a panel of experts who will give them to anyone with a good reason. They are free and open to the world. That is one of the great things about our collections.
Wow, wonderful. Well, I want to thank you again, Dr. Barbara Cohen, for coming and giving us such a wonderful talk and enjoyable Q&A. So everyone help me thank Dr. Cohen. And once again, I want to thank our sponsors, Aerojet Rocketdyne and United Launch Alliance, for making this possible, and remind folks that you can come back next month for the next lecture, which will be about the Stardust mission to bring back comet samples that could be studied in laboratories. And we'll have a guest, Dr. Scott Sanford, who will tell us all about that mission and what we've learned from those samples. So thank you very much for coming tonight. You've been a wonderful audience. Please have a good night. Thank you.